Okay, we're going to spend one more day on section 5.4, and in the problems we're going to work on tonight, the first step in those is to convert equations that look like they're non-Bessel into Bessel equations. So that way we can apply the solutions to the Bessel equations, the Bessel functions, to see if they will potentially solve these new equations. Let me walk you through this process first. The textbook doesn't do this at all, and I haven't found a good video on it, so I'll just walk you through it myself. So a general second order linear equation would be ay double prime plus by prime plus cy equals 0. Now with c, a, and b being appropriate choices, this would fall into the realm of a Bessel equation. Well, the equations we're going to look at tonight, that's not the case. You look at them and they'll look like Bessel functions, but they are convertible. Not all second order linear equations are, but some are. So if you make the suitable choice of z is equal to some function of x, and you make that replacement into this equation, what you'll get is a new equation that will fit into the form of a Bessel equation. Let me write that down to remind you. That would be something like z squared y double prime plus zy prime plus z squared plus minus p squared times y equals 0. So the suitable substitution of z for some function of x should convert this equation into this one. And then this one's a Bessel equation, so Bessel functions, depending on what p is, should be able to solve it. All right? Well, let me demonstrate to you how to go through this process of conversion. Okay? It's not too bad. Okay, so first we start by turning this function inside out. And generally these, you won't have to determine what these are. They'll just be provided to you. So we'll turn it inside out by expressing x as an explicit function of z. That'll be some sort of gz. And then we also want to differentiate this. So of course z prime will be equal to f prime of x, and then we'll go ahead and make the substitution. So we'll have f prime of gz as the argument. Okay, and that way we'll have z prime as a function of z. Okay, now let's see how we can go about performing this guy here. So we start off by determining what y prime is going to be. And of course, y prime is a chain rule because we're taking the first derivative of y with respect to x, but y now is going to be expressed in terms of z. So that's really going to be dy dz, dz dx. So I'm going to express those as y dot and z prime. Okay? So this then becomes the new variable for y prime. This is y with respect to z, so y dot will actually serve in that role right there. And of course z prime we could find once we know the substitution. All right? So that takes care of the first derivative. That's the easy part. All right? The more difficult part is what's y double prime? Well, again, it's going to be the next derivative of this. So I'm going to apply the chain rule to this. So it's going to be y double dot times z prime plus y dot times z double prime. And because that second derivative was applied to this entire thing, basically this just refers to what y prime contained inside of it, because it's sort of substituting in for y prime. So this whole thing is still multiplied by z prime for the chain rule. So this is sort of the inner product of the chain rule for y dot times z prime, and then these come as a result of them actually being part of y prime, right? Okay, so that takes care of the second derivative, and now we can start doing some substituting. Actually, let me write this out a little bit less expanded, so it's going to be z prime squared times y double dot plus, and then the second term is going to be z prime z double prime y dot. So now when it comes to substituting, I have y double prime and y prime. I can substitute them back into the original equation. So I'm going to have a times this whole mess over here. So that's going to be a times z prime squared y double dot plus a times z prime times z double prime y dot, and then plus b times y prime, that's going to be y dot times z prime, and then plus c times y equals 0. You might wonder we don't have a substitution for y, and of course y is a function of z, and we have no idea what it is now. That's the whole point of solving the Bessel equation. So we do need substitutions for y prime and y double prime, but we don't need a substitution for y because solving the equation will tell us what that is. Okay, I can clean up this middle here because they're both in terms of y prime. So there'll be a z prime squared y double dot plus, and then I'll combine all this over a common denominator. It's going to be a z prime z double prime plus b z prime, and all that's times y dot plus c y equals 0. Now this isn't ordinarily how we're used to seeing a Bessel equation. We'd like it to sort of be in standard form for a Bessel so that we'll be able to eyeball what our p-value is. So what we need to do is divide through by this leading coefficient and then make sure a z squared is occupying this spot. So I'm basically going to multiply everything through by a factor of z squared divided by a z prime squared. And once I multiply through by that, the leading coefficient is going to be z squared y double dot. The middle term, remember, has a z squared outside of this, times the same coefficient, a z prime, z double prime plus b z prime, y dot, and then the whole thing is divided by a z prime squared. And then finally the c term is z squared c divided by a z prime squared y equals 0. And then that'll be it. If you use the proper substitution into the given equation, this will now be in the form of a Bessel equation. So this final term will turn out to be z plus or minus some number. And that'll come as a result of what c is. One final trick, of course, is that a, b, and c might all be in terms of x. So you're going to have a x, you're going to have b x, you're going to have cx. If they're not constants, they'll be functions of x. And of course, you'll have to convert them over because you now have a substitution, which is x equals g of z. So a then will be a function of g of z. B will be a function of g of z. And c will be a function of g of z. So make sure you do that, otherwise you'll get a mixed bag in the end of x's and z's, and you can't have that, all right? When you're done with this, you'll be able to see what form it is in Bessel's equation. You'll be able to pull the p right out of it. You don't have to go through and solve this with the Frobenius method. We've done that for Bessel's equation. All you have to do is talk about the nature of the p-values. Okay, in the next video, I'm going to go through this exact process for question number 3 from the homework.